Applications. In general, there are three types of applications on top of Ethereum. The first category is financial applications, providing users with more powerful ways of managing and entering into contracts using their money. This includes subcurrencies, financial derivatives, hedging contracts, savings wallets, wills, and ultimately even some classes of full-scale employment contracts. The second category is semi-financial applications, where money is involved but there is also a heavy non-monetary side to what is being done. A perfect example is self-enforcing bounties for solutions to computational problems. Finally, there are applications such as online voting and decentralized governance that are not financial at all. Token system. On-blockchain token systems have many applications ranging from sub-currencies representing assets such as USD or gold to company stocks, individual tokens representing smart property, secure unforgeable coupons, and even token systems with no ties to conventional value at all, used as point systems for incentivization. Token systems are surprisingly easy to implement in Ethereum. The key point to understand is that all currency or token system fundamentally is a database with one operation. Subtract X units from A and give X units to B with the proviso, that's a word or is that a typo? With the proviso that A had at least X units before the transaction, and 2, the transaction is approved by A. I and then 2, that's got to be a typo for sure. All that it takes to implement a token system is to implement this logic into a contract. The basic code for implementing a token system in Serpent looks as follows. Look at that code. This is essentially a literal implementation of the banking system, state transaction function described further above in this document. A few extra lines of code need to be added to provide for the initial step of distributing the currency units in the first place, and a few other edge cases, and ideally a function would be added to let other contracts query for the balance of an address. But that's all there is to it. Theoretically, Ethereum-based token systems acting as subcurrencies can potentially include another important feature that on-chain Bitcoin-based metacurrencies lack: the ability to pay transaction fees directly in that currency. The way this would be implemented is that the contract would maintain an Ether balance with which it would refund Ether used to pay fees to the sender, and it would refill this balance by collecting the internal currency units that it takes in fees and reselling them in a constant running auction. Users would thus need to activate their accounts with Ether, but once the Ether is there, it would be reusable because the contract would refund it each time. Financial derivatives and stable value currencies. Financial derivatives are the most common application of a smart contract and one of the simplest to implement in code. The main challenge is implementing financial contracts is that the majority of them require reference to an external price ticker. For example, a very desirable application is a smart contract that hedges against the volatility of Ether, or another cryptocurrency, with respect to the US dollar. But doing this requires the contract to know what the value of ETH/USD is. The simplest way to do this is through a data feed contract maintained by a specific party, for example NASDAQ, designed so that the party has the ability to update the contract as needed and providing an interface that allows other contracts to send a message to that contract and get back a response that provides the price. Given this critical ingredient, the hedging contract would look as follows. 1. Wait for party A to input 1,000 Ether. 2. Wait for party B to input 1,000 Ether. 3. Record the USD value of 1,000 Ether calculated by querying the data feed contract. In storage, say this is X dollars. 4. After 30 days, allow A or B to reactivate the contract in order to send X dollars worth of Ether calculated by querying the data feed contract against to get the new price to A and the rest to B. Such a contract would have significant potential in crypto commerce. One of the main problems cited about cryptocurrency is the fact that it's volatile. Although many users and merchants may want the security and convenience of dealing with cryptographic assets, they may not wish to face that prospect of losing 20% of the value of their funds in a single day. Up until now, the most commonly proposed solution has been issuer-backed assets. The idea is that an issuer creates a subcurrency in which they have the right to issue and revoke units, and provide 1 unit of the currency to anyone who provides them offline with 1 unit of a specified underlying asset, for example gold, USD. The issuer then promises to provide 1 unit of the underlying asset to anyone who sends back 1 unit of the crypto asset. This mechanism allows any non-cryptographic asset to be uplifted into a cryptographic asset, providing that the issuer can be trusted. In practice, however, issuers are not always trustworthy, and in some cases the banking infrastructure is too weak or too hostile for such services to exist. Financial derivatives provide an alternative. Here, instead of a single issuer providing the funds to back up an asset, a decentralized market of speculators betting that the price of a cryptographic reference asset, for example ETH, will go up, plays that role. Unlike issuers, speculators have no option to default on their side of the bargain because the hedging contract holds their funds in escrow. Note that this approach is not fully decentralized because a trusted source is still needed to provide that price ticker. Although arguably, even still, this is a massive improvement in terms of reducing infrastructure requirements. Unlike being an issuer, issuing a price feed requires no licenses and can likely be categorized as free speech, reducing the potential for fraud. Identity and reputation systems. The earliest alternative cryptocurrency of all, Namecoin, attempted to use a Bitcoin-like blockchain to provide a name registration system where users can register their names in a public database alongside other data. The major cited use case is for a DNS system, mapping domain names like bitcoin.org, or in Namecoin's case, bitcoin.bit, to an IP address. Other use cases include email authentication and potentially more advanced reputation systems. Here is the basic contract to provide a Namecoin-like name registration system on Ethereum. There is the code. The contract is very simple. All it is a database inside the Ethereum network that can be added to, but not modified or removed. Anyone can register a name with some value, and that registration then sticks forever. A more sophisticated name registration contract will also have a function clause, allowing other contracts to query it, as well as a mechanism for the owner, i.e. the first register, of a name to change the data or transfer ownership. One can even add reputation and web of trust functionality on top. Decentralized file storage. Over the past few years, there have emerged a number of popular online file storage startups, the most prominent being Dropbox, seeking to allow users to upload a backup of their hard drive and have the service store the backup and allow the user to access it in exchange for a monthly fee. However, at this point, the file storage market is at times relatively inefficient. A cursory look at various existing solutions shows that, particularly at the uncanny valley 20 to 200 gigabyte level, at which neither free quotas nor enterprise level discounts kick in, monthly prices for mainstream file storage costs are such that you are paying for more than the cost of the entire hard drive in a single month. Really? Ethereum contracts can allow for the development of a decentralized file storage ecosystem where individual users can earn small quantities of money by renting out their own hard drives, and unused space can be used to further drive down the cost of file storage. The key underpinning piece of such a device would be what we have termed the decentralized Dropbox contract. This contract works as follows. First, one splits the desired data up into blocks, encrypting each block for privacy, and builds a Merkle tree out of it. One then makes a contract with the rule that every n blocks, the contract would pick a random index in the Merkle tree, using the previous block hash, accessible from contract code, as a source of randomness, and give X ether to the first entity to supply a transaction with a simplified payment verification-like proof of ownership of the block at that particular index in the tree. When a user wants to re-download their file, they can use a micropayment channel protocol, for example, pay 1 sabo per 32 kilobytes, to recover the file. The most fee-efficient approach is for the pair not to publish the transaction until the end, instead replacing the transaction with a slightly more lucrative one with the same nonce every 32 kilobytes. An important feature of the protocol is that although it may seem like one is trusting many random nodes not to decide to forget the file, one can reduce that risk down to near zero by splitting that file into many pieces via secret sharing and watching the contracts to see each piece is still in some node's possession. If a contract is still paying out money, that provides a cryptographic proof that someone out there is still storing the file. Decentralized autonomous organizations. The general concept of a decentralized autonomous organization is that of a virtual entity that has a certain set of members or shareholders which, perhaps with a 67% majority, have the right to spend the entity's funds and modify its code. The members would collectively decide on how the organization should allocate its funds. Methods of allocating a DAO's funds could range from bounties, salaries, to even more exotic mechanisms, such as an internal currency to reward work. This essentially replicates the legal trappings of a traditional company or nonprofit, but using only cryptographic blockchain technology for enforcement. So far, much of the talk around DAOs has been around the capitalist model of a decentralized autonomous corporation with dividend-receiving shareholders and tradable shares. An alternative, perhaps described as a decentralized autonomous community, would have all members have an equal share in the decision-making and require 67% of existing members to agree to add or remove a member. The requirement that one person can only have one membership would then need to be enforced collectively by the group. A general outline for how to code a DAO is as follows. The simplest design is simply a piece of self-modifying code that changes if 2/3 of members agree on a change. Although code is theoretically immutable, one can easily get around this and have de facto mutability by having chunks of the code in separate contracts and having the address of which contracts to call stored in the modifiable storage. In a simple implementation of such a DAO contract, there would be 3 transaction types, distinguished by the data provided in the transaction. 0IKV to register a proposal with index I to change the address at storage index K to value V. 1I to register a vote in favor of proposal I. 2I to finalize proposal I if enough votes have been made. The contract would then have clauses for each of these. It would maintain a record of all open storage changes along with a list of who voted for them. It would also have a list of all members. When any storage change gets to 2/3 of members voting for it, a finalizing transaction could execute the change. A more sophisticated skeleton would also have built-in voting ability for features like sending of transaction, adding members and removing members, and may even provide for liquid democracy-style vote delegation, i.e., anyone can assign someone to vote for them, and assignment is transitive, so if A assigns B and B assigns C, then C determines A's vote. This design would allow the DAO to grow organically as a decentralized community, allowing people to eventually delegate the task of filtering out who is a member to specialists, although unlike in the current system, specialists can easily pop in and out of existence over time as individual community members change their alignments. An alternative model is for a decentralized corporation where any account can have 0 or more shares and 2/3 of the shares are required to make a decision. A complete skeleton would involve asset management functionality, the ability to make an offer to buy or sell shares, and the ability to accept offers, preferably with an order matching mechanism inside the contract. Delegation would also exist, liquidity democracy style, generalizing the concept of a board of directors. Further applications. 1. Savings wallets. Suppose that Alice wants to keep her funds safe but is worried that she will lose or someone will hack her private key. She puts Ether into a contract with Bob, a bank, as follows. Alice alone can withdraw a maximum of 1% of the funds per day. Bob alone can withdraw a maximum of 1% of the funds per day. But Alice has the ability to make a transaction with her key, shutting off this ability. Alice and Bob together can withdraw anything. Normally, 1% per day is enough for Alice, and if Alice wants to withdraw more, she can contact Bob for help. If Alice's key gets hacked, she runs to Bob to move the funds to a new contract. If she loses her key, Bob will get the funds out eventually. If Bob turns out to be malicious, then she can turn off his ability to withdraw. Number 2, crop insurance. One can easily make a financial derivatives contract by using a data feed of the weather instead of any price index. If a farmer in Iowa purchases a derivative that pays out inversely based on the precipitation in Iowa, then if there is a drought, the farmer will automatically receive money, and if there is enough rain, the farmer will be happy because their crops would do well. This can be expanded to natural disaster insurance generally. Number 3, a decentralized data feed. For financial contracts for difference, it may actually be possible to decentralize the data feed via a protocol called shelling coin. Shelling coin basically works as follows. N parties all put into the system the value of a given datum, for example, the ETH/USD price. The values are sorted, and everyone between the 25th and 75th percentile gets one token as a reward. Everyone has the incentive to provide the answers that everyone else will provide, and the only value that a large number of players can realistically agree on is the obvious default, the truth. This creates a decentralized protocol that can theoretically provide any number of values, including the ETH to USD price, the temperature in Berlin, or even the result of a particular hard computation. Number 4, multi-signature escrow. Bitcoin allows multi-signature transaction contracts where, for example, 3 out of a given 5 keys can spend the funds. Ethereum allows for more granularity. For example, 4 out of 5 can spend everything, 3 out of 5 can spend up to 10% per day, and 2 out of 5 can spend up to 0.5% per day. Additionally, Ethereum multisig is asynchronous. Two parties can register their signatures on the blockchain at different times, and the last signature will automatically send the transaction. Number 5, cloud computing. The EVM technology can also be used to create a verifiable computing environment, allowing users to ask others to carry out computations and then optionally ask for proofs that computations at certain randomly selected checkpoints were done correctly. This allows for the creation of a cloud computing market where any user can participate with their desktop, a laptop, or a specialized server, and spot checking together with security deposits can be used to ensure that the system is trustworthy, i.e., nodes cannot profitably cheat. Although a system may not be suitable for all tasks, tasks that require a high level of inter-process communication, for example, cannot easily be done on a large cloud of nodes. Other tasks, however, are much easier to parallelize. Projects like SETI at home, folding at home, and genetic algorithms can easily be implemented on top of such a platform. Number 6, peer-to-peer gambling. Any number of peer-to-peer gambling protocols, such as Frank Stahano's and Richard Clayton's CyberDice, can be implemented on the Ethereum blockchain. The simplest gambling protocol is actually simply a contract for difference on the next block hash, and more advanced protocols can be built up from there, creating a gambling services with near zero fees that have no ability to cheat. Number 7, prediction markets. Providing an oracle or shelling coin, prediction markets are also easy to implement, and prediction markets together with shelling coin may prove to be the first mainstream application of Futarchy as a governance protocol for decentralized organizations. Number 8, on-chain decentralized marketplaces, using the identity and reputation systems as a base.